Hello 171 class, this is your notes for part 1 of section 3.4. We're going to talk about exponential log equations. In this first part we'll talk about exponential equations. So an exponential equation is an equation that has a variable in the exponent. So it's got something that's exponential on one or side or both potentially. But for several of these it'll just be one side. We will look at an example if it's on both. Shortly. Okay, so when I have an exponential equation, different methods that we can use to solve these things. The easiest, if you can do it, if it can be used, the easiest method is to rewrite both sides of the equation with the same base. So in this problem right here, example 2 part A, 2 is the base on the left side, but 16 is the base on the right. They're not the same base as it stands. But 16 is equal to 2 to the 4th power. And so then I can actually write this in this form where the left and right side both have the same base. Alright, so I have 2 to the 3x minus 8 equals, instead of 16, I'm going to write it as 2 to the 4th. Well, because both of these now have the same base, what this says is if the bases are the same, then you don't need the base anymore. You can get rid of the bases, so I can drop this 2 and this 2 out, and then my equation becomes just 3x minus 8 equals 4. This exponent equals this exponent. M equals n. And then we just solve this linear equation. We add 8 to both sides, the 8's cancel. We're left with 3x equals 12. Divide both sides by 3, we get x equals 4. And there's our solution. We can easily check it by plugging the 4 in for the x right here, which I've done here, and then enter, and we get 16, so we know that it works. Okay, so if you can change both bases, it's the easiest it's going to be. Okay, with our second example, 27 and 9, again, different bases, but I can write both of these as 3's to powers. I can't write 27 as 9 to a power like we did last time, but both of them can be written as 3 to a power. So I'm going to do that. Alright, 27 is 3 to the 3rd, 9 is 3 to the 2nd, so I end up with both of these. Now, same base, so once again, I can get rid of the 3's as the bases, and I end up with 3 times x minus 3. I'm going to have to put a parentheses in here on this. But that gets to come down here, and then 2 times x minus 1. Once again, I need a parentheses around this old original exponent. But because the way we multiply exponents, when we do powers to powers, I end up having this equation once I drop the base on both sides. I get 3 times x plus 3 equals 2 times x minus 1. Now I distribute. Alright, I get 3x plus 9 equals 2x minus 2, and then this is just a linear equation to solve. Alright, and then there is the solution, x equals negative 11. Go back to the original. You can plug in negative 11 for the x. On the left side, you get this number. You can plug in negative 11 for the x on the right side, you get that same number. So again, you know it's correct when you check it, and you get the same thing on the left as you do on the right. Alright, bringing in the logs, another method, completely fine method, but if you can't do this, if you can't change the base on both sides and get something easy, I mean, you can always change the base. That's the change of base property, right? But you can't change the base easily. Like this is not the power the same as this. These two aren't powers of the same base. Then you have this method, bringing in the logs, which will work on this as well. It would still work here. It's just if the bases can change easily, then change the base. If they can't, that's when you bring in the logs. So the first thing we're going to do is isolate the exponential expression, and then we're going to use this property that if the two things are equal, then they're equal when we bring logarithms in on both sides. So we're going to either take the common log or the natural log of both sides if the bases are other than 10. Okay, so this idea is the natural log of b to the x. We'll be able to bring that x down in front, and we'll be able to solve for that x. Okay, because when we're solving exponential equations, we want the variable that's in the exponent, and that's one of the properties of logs, is the exponent can come down. And then we've got multiplication that we can use to solve for that x. It becomes a linear equation, basically. Alright, if you have e's or base 10s as your exponential part, then just remember that you can just bring in logs and then it just wipes it away and you've got x. Okay, but if it's any other base, you bring in the natural log or even the common log, you bring down the x to help come up with a method to solve it. Alright, let's look at this one. 4 to the x equals 15. Okay, I can't easily change 15 to 4 to a power. I can using logarithms, but if I'm going to use logarithms, I might as well just bring in logs. So I bring in logs. 4 to the x, 15, what was originally equal, is now inside a logarithm. Okay, now after I do that, I can bring down the power. I can bring down the x out in front of that ln. And then now that I have multiplication by the variable that I'm solving for, I can just divide this away. This is just a number. I can divide it away on both sides of the equation, and I end up with x equals the natural log of 15 divided by the natural log of 4 for my solution, which is approximately 1.953. Okay, and I can check it by typing 4 raised to this approximation 1.953, and I get something really close to 15. Now, to get exactly 15, I would have to put 4 raised to the parentheses and type this in exactly. Natural log of 15 divided by natural log of 4. And if I do that, then yeah, I'll get exactly 15. Okay, but it's just longer to type it out. So to check it, if you want to use a decimal approximation, that's fine. Alright, this second one has 10 to the x equals 120,000. So this is where I would just use the common log. If it's 10 to the x, the log and the 10 to the x and the common log wipe each other out, and you just end up with x. So in this case, I'm going to take the common log of both sides. And remember, common log is base 10. So that 10 and that 10 and really that log all go away, and I end up with just the x is the only thing that's left. So there's the exact answer, the log of 120,000. But a lot of times we'll be asked to approximate that. And to do that, we just type it into our calculator and round it to wherever they tell us to round. Alright, now check again. It's easy to check these things. You just have to understand that when you type in an approximation, 5.079, you're going to get close to 120,000. You're not going to get exactly unless you type in literally that expression. 10 to the log of 120,000. Now I get exactly 120,000, but if I type in a decimal approximation, I'm going to get a decimal approximation to the answer. Alright, here's another example. This one, we got the x in the exponent that we're solving for, so that's an exponential equation. And remember, we always are going to start these by isolating the exponential part. So this e to the 0.6x is exponential. This other stuff, the 40 and the 3, I'm going to move over to the other side to get the exponential part by itself. Alright, so I add the 3 over, I get 40e to the 0.6x equals 240, divide both sides by 40, that gives me e to the 0.6x equals 6. Okay, this is what I mean by the exponential part being isolated. Right, that's when we're going to bring in the logs, once the exponential part's isolated. And remember, if e is involved, right, the natural log will just wipe that e out and just give us x. So in this case, I would definitely bring in the natural log. Alright, on the left side, the natural log and the e are going to wipe each other out and just bring that exponent down. Alright, then I'm going to divide both sides by the 0.6 that's in front of the x, which is obviously going to get rid of that 0.6. And then I have my exact answer. X equals the natural log of 6 divided by 6/10. Okay, and then if I want an approximation, I just type that into my calculator, that exact expression, and get a decimal approximation. Okay, now this original expression is a little bit more, not much more, but a little bit more complex than the previous few. So in this case, a good idea would be to use the STO feature, store. And you can store your answer as x. right? Whatever the variable name is. And then you literally just retype the original side, left side and right if it's two different expressions. But the right side here is just a number. But I just type in 0.6x, right? Close the parentheses minus 3, and then I get exactly 237 out. So again, I know it's correct. That's a nice way to check using that STO feature on your calculator. All right, last example. So this one we've got an x on both sides, and not only that, we also have bases that can't be written as the same base to different powers. So we're going to bring in the logs in this, but unfortunately when you bring the logs in this, it really becomes an extensive algebra, testing your algebra abilities basically, because you're going to have to distribute, you're going to have to factor. It becomes a tough problem, but these are always done the same way. So the good thing is once you get it down, you always have it down. So the first thing we're going to do here, we can't isolate the exponential part because there's exponentials on both sides. So we're just going to go ahead and bring in the logs as it is. Alright, and then because we brought in the logs, we can bring these powers down. Alright, so I bring the powers down out in front using the power rule back in 3.2. And once I've done that, now these are numbers, right? And the log of 5 is a number, the log of 4 is a number. I can actually distribute those back into this expression. So I'm going to have x times the natural log of 5 minus 2 times the natural log of 5. And then similarly on the right side, I'm going to distribute that natural log of 4 through. So after I've distributed it, there's the natural log of 5 times x. There's the negative 2 times the natural log of 5. There's the 2x times the natural log of 4 plus 3 times the natural log of 4. So I've just distributed these logs through on the left and right side. Now, my goal is to get the things that have the x's together on one side and the things that don't have x's together on one side. It's no different if this had been something like 5x minus 10 and 8x plus 12. All right, if I had that expression, I'd group the x's on one side, I'd group the numbers on the other. No different here, it's just the numbers in front of x and the constants have logarithms involved. All right, now I'm going to subtract 2x natural log of 4 from both sides so I can have the x's together on the right side. Okay, so these all three combine here. Now the only thing left on the right is 3 natural log of 4. Alright, and now I'm going to add this minus 2 natural log of 5 away. So now I only have x's over here on the right, left, and then I have only things with constants, no x's on the right. Alright, so this is where I'm going to go down, give myself a little more room. Notice here on the left, there's an x in both of these terms that are being subtracted. So it has a common factor, a GCF. So what I end up doing here is I'm going to factor this common factor out, which leaves x, the common factor, times the stuff that's left over, natural log of 5 minus 2 natural log of 4. And now I only have that one variable, and it's being multiplied by this equal to this other number. So just like if this had been 5x equals 15, I divide both sides by the number in front of x. Same thing, divide both sides by this number being multiplied by x. Alright, and so x equals 3 natural log of 4 plus 2 natural log of 5, all divided by the natural log of 5 minus 2 natural log of 4. There's the exact answer. Alright, it's an ugly answer, but it is the exact answer. And then if we plugged it into our calculator, we could get a decimal approximation for it as needed. Just notice again all the parentheses we need because we have addition and subtraction in the numerator and denominator. We need parentheses around the top and the bottom to be able to get a decimal version of this number. Alright, so again, it's not a pretty process and it's definitely not a pretty answer, but if you have an exponential equation with different bases that can't be expressed as a same base on both sides, this is what your answers are typically going to look like. They're going to have multiple logs, and it's just an ugly expression. Now, yeah, these can be combined and simplified, but you don't have to. You can keep them in this form. and you're not expected to simplify these unless you just want to. If you do, you'll get credit for it, but just know that this is fine to leave it in this form.